My topic here is on biodegradation of polystyrene and polypropylene by Bacillus subtilis. So using the influence of temperature and growth media as um, using the influence of temperature and growth media. These are the two parameters I'll be looking at in my poster presentation. So I have 4 objectives there, which the first objective to measure the weight loss of the polystyrene and polypropylene plastic, to analyze the chemical structures using FTIR spectroscopy. So to assess the ultrasound crystallinity using the SRD, although in this particular poster, I did not include that because of space. That's for the XRD. And the fourth objective is to evaluate the changes via surface morphology using the SEM. So the aim of this work is to investigate the biodegradation of polystyrene and polypropylene by Bacillus subtilis under the influence of varying environmental conditions. So we all know plastic waste accounts for a significant environmental challenge. So only about 9% of these plastics are being recycled, while the others accumulate in the environment, causing environmental challenges. So certain microorganisms like bacteria and fungi have been studied to see their influence on degrading most of this plastic in the environment. So what we'll be looking at here is the use of bacteria, Bacillus subtilis, for this biodegradation. So in our methodology, we used two nutrient media, that's the broth and the agar, as our nutrient source for the bacteria. So our temperature conditions were varied at 15, 25, and 35 degrees for 56 days. That's 8 weeks. So after this, we took our average weight loss of this plastic waste. So if you look at the first figure there, for the average, that's the average weight loss of the polystyrene and polypropylene in nutrient broth media. That's the first figure. We can observe that after 60 days, that's the 8 weeks, week 8, because we did 56 days, that's 8 weeks. So
Okay. I am sure that Obed will join us soon. I think Glo is really showing him a lot. Okay. I can see that Obed is back. I don't know if you can hear us or if you can hear me.
okay, I can hear you guys now. Sorry.
Okay. Yes, please go ahead.
Okay, so the first figure, we can observe that the weight loss of both the polypropylene and the polystyrene was increasing with increasing temperature and time. So if you look at the figure, you can see that the weight loss is fluctuating. That's because what we did in this particular study of varying temperature and time was that we took the average weight loss of each week. So the average weight loss of each of the plastic was taken for each of the week, and we can see that the highest weight loss was observed at 35. Sorry, I think that's the temperature figures are a bit low, so you guys can't see it. But at 5 degrees, the weight loss of polystyrene, the highest weight loss of polystyrene was observed, which is around the 8th week at 56 days. And the lowest weight loss was observed at 15 degree. So in the figure 2, the second figure there, that's for the weight loss at in nutrient agar, you can also see that the um, higher weight loss was observed at 25 degrees, while the lowest weight loss was observed at around um, 15 degree also. So this shows that the higher the temperature, the higher the weight loss of both polymers. So this is likely due to the increase in activity of the bacteria at higher temperature. So for the FTIR figure there, which is the second figure, we can observe that. So we can see the controls, which the control for the polystyrene, which is the first one. So for in broth at 25 degree, you can see changes in the uh structural um changes in structures in the FTIR of this polystyrene at 25 degrees. So that arrow there with a curve shows that there is an OH group that is being increased, that the intensity of the OH group is being increased. And this is likely due to the enzymatic activity of this broth, because the enzyme that we likely link this activity to is a hydrolase enzyme, which contains an OH group. So because of the increase in this OH group intensity there, we can link this activity to an hydrolase enzyme. Although this is a preliminary study, we are still also trying to see how we can isolate the enzyme responsible for this biodegradation. And also, we can also observe that OH peak at the polypropylene agar at 25 degree also. So we can see that at 25 degree, so for the PS is at 35 degree in broth, while for the polypropylene is at 25 degree in agar. So you can see that there is an enzymatic activity acting on this plastic with the increase in this OH peak. So we can see in the surface morphology, you can see how these plastics are being broken down by this bacteria that we use. So if you look at the images, you can see some rough porous surfaces. So this is due to the activity of the bacteria on these polymers that we use. So for the polypropylene, we can see that it has more um, cracks and rough surfaces. So we can link this to the fact that the polypropylene is more susceptible to the attack of the bacteria than the polystyrene. So from what we concluded in this research, we can observe that optimal degradation was observed at 35 degree. So at 35 degree, in the average percentage weight loss, we observed that at 35 degree, the weight loss of this plastic was more significant than at lower temperatures like 15 and 25. So the media also play a role in improving or improving the biodegradability of this plastic. So if we look at the structural changes, we can see in agar, there is more uh, in agar there is more changes in the structural formula of this plastic. In FTIR, we can see in agar that's for polypropylene, there is a more significant change in the FTIR compared to in broth. The intensity in agar is more higher than in broth. So we can say that the bacteria performs better in agar media than in broth. So the our future work, we are trying to look at the efficiency of or the efficacy of other microbial strain and see how we can isolate the enzymes. Can you guys hear me? Sorry.
Yes, we can. You can go ahead.
Okay.
We can.
So we can see
Yes.
how we can isolate. We can see how we can isolate the enzyme that is that is responsible for this degradation. So the enzyme like I said earlier, the enzyme we've linked this to is the hydrolase enzyme because of the peak intensity of the OH group in the FTIR. So that's all for the poster presentation. And I'm very sorry for the delay because of my network.
Okay. Thank you so much, Obed, for that wonderful and enlightening presentation. So you already have questions.
Okay.
Abdulhafiz Akinloye is asking that how was the influence of water controlled to avoid IR interference? Okay, I
How
don't
was
know
the
if you got it.
influence of I did not get that question really well. Sorry,
Okay,
can
let me repeat it. How was the influence of water controlled to avoid IR interference?
okay. We didn't really use like for sterilizing of the plastic, we did not really use water. We used absolute ethanol, and we also dried this plastic at 50 degree in oven to remove any moisture from it, so that to avoid the influence of water in to control the influence of water in order to avoid its interference with the air. So we tried to reduce as much moisture as possible in this plastic. So we dried them in oven at 40 to 50 degrees.
Okay, thank you. And you have another question from Abdulhafiz saying that were there subtle differences at the IR fingerprint region?
Okay, for the fingerprints region, we like where if we're reading the IR spectrum, the fingerprint region don't really matter a lot. We focus more on the CH region, the double bond region, and triple bond region, because the fingerprints region will always be CH. So there won't be really any difference in the fingerprints region. What we'll focus mainly is the um, double bond, the single bonds OH or OH region, and the triple bond region. Because even if we look at the fingerprints, because we are using the fingerprint will always be the same as the control of the plastic. I don't know if
Thank you.
this answered that question.
Thank you very much. Abdulhafiz, I hope your questions have been answered. I don't know if you can just give a reaction. Okay, so while we wait for Abdulhafiz to react, you have another question from Ololade Gbadebo. She's asking, incubation was for 56 days. Did you study the growth curve of the bacteria to ascertain their viability over those many days?
Okay, we did not study the growth curve of the bacteria, and secondly, we didn't leave the bacteria for 56 days like that, because we did a test run. We left the bacteria for 1 month, and they all, like in agar, the agar dried up. So what we did was that after every 2 weeks, we always put in more, because our focus now is on the plastic and not the bacteria. We've already known that this bacteria will not last that long, most especially at 15 degrees. They will all die off. So after 2 weeks, we always put in more nutrient agar and or nutrient broth, and we insert 5 ml of our cultured subcultured bacteria. So that's why we took the average weight loss of each of the plastic. So assuming we did, assuming we are just looking at the weight loss, you see, if you look at the graph, you will see that it will be decreasing. So we just checked for the percentage weight loss, average weight loss every 2 weeks. So we did not do a growth curve of the bacteria because every 2 weeks we still renew the nutrients and also the bacteria